Okay, so page 2 of the introduction. Just a little bit more about an embedded computer system or embedded system. So I said earlier it's part of a larger system. So an embedded computer system, it plays a dedicated role. It has a dedicated purpose, unlike a general purpose computer system, and it has purpose-built hardware and software. So probably you'll create the printed circuit board and populate it with the components and put it in the product, and then you'll create custom code that will run on it and probably won't change for the life of the product. Now, the real-time system. So I said that it has deadlines. Basically, real-time systems, they respond to events or react to events. So real-time systems react to, and I'm going to color this just to make it stand out. React to events, and that must be within a certain amount of time. So they must react by a deadline. Guess I can color that too. Okay. So deadlines have a range of how important they are, and so we've got a hard deadline, and missing it is going to result in system failure. So for example, anti-lock braking system. If it detects as an input that the wheels are locked, they're not rotating at all, and you're still moving, it should be starting to pump them, and if it doesn't start that soon enough, you can have an accident. So, or things could be more catastrophic than that even. You could have a meltdown in a nuclear reactor, heart stops beating with a pacemaker, that kind of stuff. So system failure. Now at the other end, and what we've got here is a continuum. At the other end we have soft deadlines. So missing a soft deadline means that you're going to have degraded service. So the system continues to function. So the classic example of this is streaming audio. So I was looking this up earlier, and it will depend on the encoding and the protocol, but when you're streaming audio, you're looking at something like 50 packets per second. And if one of those goes missing, which can happen, we're going to look at networking later in the course, or if they arrive out of order or something like that, but let's say one goes missing, so it's missed its deadline or it arrives late. You might notice a bit of crackling or static in the audio, but it's not the application can keep going. So I guess another point to make with embedded systems is that the importance of temporal correctness equals the importance of logical correctness. So you're used to writing programs and you test them to make sure that when you give them the right input, they generate the right output. With temporal correctness, you want to make sure that things happen at the right time. And usually it's not good enough to just run some test cases. That's not going to prove that. Timing things can be, timing errors can be hard to find. So it needs to be proved analytically, and we will do that when we get to the scheduling part of the scheduling unit of the course. Okay, and just 2 more things here. An operating system. So the most common operating systems that well, actually there's quite a few, but for personal computers, we've got Windows, we've got Mac OS, and we've got Linux, and they all have a lot in common. If you think about an operating system, what does it do? It controls your interaction with the computer, it decides what runs when, that kind of stuff. And an operating system, it manages computer resources. At the heart of it, that's what it's doing. So types of resources it might manage, what do you think that might be? So I set the screen, so it's going to manage your I/O devices, usually through using I/O drivers. It will manage which program runs on the processor when. So it manages the processor. It manages memory. So we're going to learn about the virtual memory system when we talk about computer systems. And so it can put in place protections so that one program can't accidentally or maliciously interfere with the memory from another program. And we also have timers. There's a system clock that it manages. A special type of I/O device is the network, which is also managed by the OS, and the file system. Okay, and so an operating system really consists of the kernel, which does all this managing that I've just talked about, and then has a bunch of utilities built around it, like your windowing system, and shells that you can, like a terminal that you can type stuff into, and all that kind of stuff. So together, that's your operating system. Linux, for example, Linux is technically just the kernel, which schedules when processes and threads run and that kind of stuff. And then usually it comes packaged with a bunch of utilities, a lot of them developed by GNU, the Free Software Foundation. So technically it should be the Linux GNU operating system, but we just all call it the Linux OS. Okay, so operating system, I'll just call that an OS from now on. And then this course is an introduction to computer systems and real-time operating systems, or real-time scheduling. I forget what the name of the course is. It's too long. Anyway, so real-time OSs, usually we call them RTOSs. They provide these other services that I just mentioned that operating systems do, but in addition, they have to do one thing. So if you look back at the diagram that we started with, it's all about deadlines with real-time operating systems. So for real-time OS, it must be able to guarantee deadlines. So typically they'll specify, well, for a given processor it can specify when an event happens, how long until, say, the interrupt service routine is running, that kind of thing. And anyway, so the way real-time OSs are built, you can do an analysis of an application and say, yes, this will definitely not miss any deadlines, or maybe it will sometimes. So, okay, that's the end of the introduction unit, and next will be the computer structures or computer systems unit.